All right, so maybe 8 p.m. is a bad time to do a live because no one's here, but that's okay. I'm still going to go through my lesson. Things come up, I get it. So we have two sections that cover linear functions. There's a section that just talks about equations of a line and all the definitions, and then there's a section on applications. And so I'm kind of going over both. I'm going to go through all the definitions, and then I'm going to do an example that's an application problem where you are basically applying all of the definitions. And then hopefully you can see kind of a real world application and it makes sense and see why this is so important. So we've been solving linear equations, which are just for x. They don't have any exponents. They don't have square roots, things like that. Those have been one variable equations. Once you get into graphing, that's when you have two variables, and you have a linear equation in two variables where you have an x and a y. So we have our definition of a linear equation with x and y is ax plus by equals c, where a, b, and c are real numbers, positive or negative. Most of the time, a and b, we like to have those positive and whole numbers, but it's not a requirement. And they're not zero, basically. So our linear equation is ax plus by equals c. The key is, just like a linear equation, in one variable, there's no exponents. It's the same thing in two variables. There's no exponents on the x or the y. When you have x and y on the same side, that is what we call standard form of the equation on a line. Some special cases of standard form is a vertical line, where you have just the x part, ax equals c, or a horizontal line, where you have just the y part, by equals c. And the coefficients of a and b may be 1, there may be no coefficient. We generally solve for x or solve for y when we're writing the equation for a vertical or horizontal line, but you could see equations not solve for those variables. And if it has only x or only y, graphing it will have a straight line, either vertical or horizontal, depending on the variable. So there is something called slope of a line. Slope is a number. It doesn't have units in a typical equation. If it's a real world situation, there are units to slope, but it's a numerical value that indicates the amount of slant of a line. So the larger the number, the more slanted it is. The smaller the number, the less slanted. It also indicates the direction, whether it's moving up or down as you move from left to right. Positive slopes go up, negative slopes go down. So if you ignore the sign and just look at the number, the larger the number, the steeper it is. Slope is also called a rate of change because it's basically telling us how much something is changing. That slant is how much does it change as I go up, as I move right, how much does it go up? So it's amount of change. And calculus is the study of rates of change. So you can think of calculus as basically studying slopes for things that are not lines. It's studying the concept of a slope, but for any kind of graph. But the terminology slope is typically just used for lines. So here's a chart basically that shows the form of a line, ax plus by equals c. Positive slope, as you move left to right, it goes up. Negative slope, left to right, it goes down. A horizontal line has a slope of 0 because there's 0 slant to it. And a vertical line has an undefined slope because basically the slant, the steepness is infinite. So it's really important to know what slope means, what the slope tells you about what the line looks like, and then what the equation looks like. So I mentioned the y equals and the x equals for horizontal and vertical lines. Those are really important and they relate to slope. So to actually find slope, we have, of course, an equation. And we indicate slope by the letter m. It's a lowercase m. Uppercase m means something else, so the capitalization does matter. So lowercase m, we say that slope is rise over run. Rise means how much you go up. Run is how much you move to the right, basically. Because because it's measuring your change. How much are you going up as you go over? The abbreviations for this, and so you see these little triangle symbols. This is the Greek delta. It's a capital delta. It's a Greek letter. Lowercase delta looks something different. So it is a capital delta. And we usually use this to indicate change in or change. So it's an abbreviation that we use to just to indicate how something changes. I don't know the history of that particular symbol to represent change, but it does. There's a link at the bottom here, so when you click on the PowerPoint, you can go to that link, and it talks about the history of the symbol M, why we use the letter M. And there's not really a clear history. It's one of those things that we don't really know, but we have some ideas. So delta y over delta x just means the change in y over change in x. And we measure change by the difference or the distance from one y value to another y value. So to find the distance between points, you just subtract them. It goes back to the distance definition of absolute value is the distance between two things, and you may be like doing some sort of subtracting between zero. Here we're just finding the difference between two values that tells us the distance between them. It's just a way of measuring. It's, you know, if you think of it in terms of units, and you have GPS coordinates, you know, if you subtract them, they'll give you maybe miles or something like that. So our measurement for change is just literally subtracting the y values and the x values. The key is you have to subtract it in the same order. So conventionally, we do y2 minus y1 over x2 minus x1. So those lower numbers are subscripts. Those are just labels. So we're just labeling points as like the first order pair and the second order pair, and you're subtracting. But you need to make sure you subtract in the same order. If you flip-flop the order, if you put x on top instead of y, you can kind of start messing things up. When I was learning slope, my teacher told me to remember to y's up. Basically, that y is up and it's on top of the fraction. So that's something that I've just always remembered. It's also good for graphing to remember that y is the up and down on a graph. So we have this formula to determine slope, and we use the letter m. And so the absolute value, basically, if you ignore the sign, that's a big number, it gets more steep. You know, the steepness increases. So you can see here, so going back here, we had a zero slope and an undefined slope. Now you can see where that comes about because we're dividing. And if you divide by 0, which means that there's no vertical change, or no horizontal change, I'm sorry. X is horizontal, so if there's no horizontal change, as there is on a vertical line, it doesn't go left or right, then your denominator is 0, you're dividing by 0. So that's how we get an undefined slope. Now, if there's no vertical change in a horizontal line, it's only going left or right. It does not go up and down. So the top of your fraction is 0. 0 divided by anything is 0, and that's how you get a slope of 0. And then if your slope is positive, if it's greater than 0, it's basically going up as you move left to right. And then if you have a negative slope, it's going down. So this is the same information on this chart here. We're just giving it in terms of m as the actual value for slope. So it gives you a lot of information about the shape of the graph without even graphing it. So you have an idea of what your line is going to look like. And then you can even use slope to compare two lines to see if one's steeper than the other. And with that, you can even use slope to compare if lines are parallel, because they'll have the same steepness, so they won't intersect, or if they're perpendicular. And there is a special formula for that to determine if they're perpendicular. So there are other ways to write the equation of a line other than standard form, where x and y on the same side. We have what's called slope-intercept form, and that is y equals mx plus b. So m is the value for slope, and then we indicate the y-intercept, where the y value is b. If we wrote that as a function, it's f of x equals mx plus b, because f of x and y are interchangeable when you have functions. And if you don't have a slope, if it's just f of x equals b, that's something we call a constant function, because you just have a horizontal line, your y value is not changing. So slope-intercept form is used a lot when we're graphing. That's the most common way we give equations of lines. So that's what you'll see most of the time. The third way we can write a line is called point slope form, and that is y minus y1 equals m times x minus x1. And for point slope form, you need a point and a slope, hence the name of it. Point slope form is really nice to start with, and then you solve for y to put it in slope intercept form. So point slope form is used a lot for writing equations, and then we will do some manipulation to put it in slope intercept form. So some common applications of equations of lines. You'll use this a lot for predicting data that generally goes up or down in one direction, so there's not a lot of up and down movement. So if you have a whole bunch of data points and it look like they could be in a line, or even if they're not exactly in a line, they have like a linear trend where they kind of are going in the same direction, even if it's a very thick line, you can use an equation for a line to kind of, for prediction purposes. It's not going to be exact because it's real data, but it can give you some information. Lines, the equations of a line, because it has a rate of change, and what's special is that the slope, which is the rate of change, it is constant, so it doesn't change. It's changing by the same amount. That's really good for hourly income, because if you get paid $9 an hour, it's not $9 1 hour and then like $10 another hour, then back to $9 again. You know, like that. It's a flat rate. It's the same rate every hour. That's the slope. So anything where you have a flat rate of something per hour, that is great for using an equation of a line. And it doesn't have to be per hour. You could have something similar if you get paid per item, like if you are selling something, anything where you have a set number per something else, that basically indicates that it's going to be a linear equation. So something or something generally indicates it can be linear, especially if the amount is not changing. So a lot of things tend to be linear equations. Just most real-world applications tend to actually be linear. They may not be exactly linear, but they have this common trend of being linear. Related to hourly income is just in business in general. A lot of cost equations, revenue equations, and profit equations are linear. And that's because your cost, usually you may have a flat cost, which we have as our y-intercept, essentially, the cost you pay no matter how many items you produce. And then it costs you some amount to run a machine per item you make or per hour. And so you have that per going on, and so that's a linear. And same thing with revenue, revenue usually doesn't have a flat income, but it will have a flat amount you make per item that you sell. And so then you have that slope going on, so that's linear. And then profit is just simply subtracting revenue minus cost. And so you're subtracting a linear equation from another linear equation, you're still going to be linear. So a lot of those business applications are linear equations, which is one of the reasons why algebra, where we cover this, is required for business. And then any relationship that can be written with a proportion. So a lot of unit conversions, you can do those, write them as linear equations instead. One example of this is actually converting between Celsius and Fahrenheit. It's actually a linear equation. It's a unit conversion, and you can write it as a linear equation to do the conversion. So that's another application. And these are the things that you see most often. So once you get used to what these mean, you're like, okay, anytime I see this, I need to write an equation on the line. So here's where we're going to get into a real world situation. And so I've actually pulled real data here, and I have the link And let me click on it so I can actually pull it up for you. So I have a link. There's a website called statista.com. Wonderful website. I recommend. There is going to be a discussion, I think maybe it's this week. I get confused what week it is, but there's a discussion where you have to get real data. So this is real data. They've even projected it out. And you might be wondering, well, how do they come up these guesses for 2029 to 2030? Because that's like 10 years from now. Well, they're doing exactly what we're going to be doing, is linear. They're going to see the pattern, see that it's a line, come up with an equation, and then use that to project for like the next 10 years. So they're doing exactly what we're doing. But this has data all the way back to 1950, and this is the number of bachelor's degrees earned in the United States by gender. So if you highlight it, so the dark blue, it's kind of hard to see on here, but the dark blue is female, and then the light blue is male. So you can see that females have been getting more bachelor's degrees than males. But if you go back in history, it was the other way around, and that was mainly because there was a time when women couldn't go to college, or it wasn't expected. So you can see that it was the other way around, and then it started flip-flopping, and now this is the pattern. And it's not a perfect line. You can see that it kind of curves, but what I did is I actually put this on a scatter plot, an XY plot. A scatter plot is when you just have dots and you're not connecting them. And so that is the second link that I have here. So I entered in the data, and I just did 2002 through 2018. So I don't have everything. I just did past 16-year period. I could do the last 10 years if I wanted, but I just wanted to get a good... Oh, it didn't update. I swear I had saved it and updated all of my points. Wonder if I can attempt recovery. There we go. Thank goodness. Okay, I'm going to make sure I save. Okay, so I had actually added points. So you can see that this is a scatter plot because it has dots and they're not connected, but it basically forms a line. It's not a perfect line, but it forms a line. And if it looks like a line like this and it's close, that's where we want to use a line for prediction. And so we need to get an equation of a line. So this is a real application where you might be like, hey, a line equation would be good for this because it looks like a line. So my data, I chose just the women's bachelor degrees. So just the female, not the total or anything like that. And so I just have the table here. So we're going to go through the whole process of what you would do in a situation like this. And this is something that you could do if you're running a business. If you have a whole bunch of data and you want to see what the trends are, you would go through this process. So what we're going to do is we are going to approximate a linear equation to make a prediction. It's not going to be exactly right. It's a prediction, and it uses data. And we can't use every point because it's not a perfect line, but we're going to try to use as many points as possible so that it fits most of the points. So we're going to draw by hand what is called a best fit line. And so I copy the graph here, and I literally have a ruler that I am using on my tablet, and I'm going to try to hit as many ordered pairs as possible. It's a little difficult, like the bottom part up to like 2012, I guess 2011, that looks very straight, and then there was a jump, and then it's like a second line. Like, they're not perfect. What I'm going to try to do, I go through the bottom points. I'm going to try to eyeball and go through maybe between them, see what I can do. So I'm using a ruler, but it's not perfect. So I kind of used my ruler to draw a line, and you can see it hits almost every point on the lower part, not so much 2012 through like 2015, and then it kind of hits it again. So we might have some points that are kind of unusual, and then it fits the trend. So I just drew this line, and this is my best fit line by hand, basically trying to make it hit as many points as possible. So you need to draw lines so we can get an equation, and we want to choose two ordered pairs on the line. We want them to be on the line. So, and you want to try to pick easy points. So I actually went through a point right here. So that's my 2008 number. And so I'm going to have to look at my table to figure out what the point that is. But since it went through my point, that's a good one to pick because it's on my line. And then I'm going to look at my line and see, is there something that looks really easy to read off of on my line? You know, you want to try to have it on the grid because that's really easy. It looks like I could actually almost use this point or that point because they're really close. I think the second one might be best. And also, it basically looks like I'm hitting one of my points, so I can use that ordered pair. So I'm trying to read, that looks like it's 2017, and then whatever the Y value is. So I'm going to actually go to my table and use those exact points. But if I wanted to, I could have picked something like I could have used this point right here. I would just have to estimate what the Y value is. So if possible, pick any real order pairs that are on the line because those are going to be more exact. But if you drew a line and it doesn't go through any point, you can pick something else as long as you estimate what the Y value is and your X value. So you draw your line, you basically pick 2 points. Then what we need to do is find the slope between those 2 points. So we use those 2 ordered pairs to get the slope, which is going to measure the steepness of the line. And then we use the slope in one of the ordered pairs to get the equation of the line. And we're going to be using that point slope form I talked about. And then we will then have an equation that we can use to predict. So like maybe I want to predict for 2020, and then I can even double check and see, hey, does that match what that website predicted? You know, we can see how good is my prediction, you know, who has the better line. So that's what we're going to do. So first step is to find the slope. And that starts with the ordered pairs. So I need to, let's see, get my pen out. So I had, oops, I'm in highlighter. That is no good. Okay, so going back to my graph, it was 2008 and 2017 were my 2 points. And I need to fill in the Y values. So I'm going to go to my table that I have. So 2008, read it off the table, 895, 2017, 1120. So 895, 1120. And then I'm going to go just double check that I wrote those right, 895, 1120. Good. So that's the first step, is just to write down your ordered pairs. And I'm going to label these because I'm going to be using like X1, Y1. So my first one is going to be the first ordered pair. So that's going to be X1 and Y1. And then X2, Y2. So next, after that, you want to find the slope. So I have the formula here, Y2 minus Y1 over X2 minus X1. So we have M equals, and then I need to plug in my numbers. So Y2 I have labeled as 1120. Y1 is labeled as 895. So that's the top, and then in the denominator, the bottom, we've got 2017 minus 2008. So you have to make sure you're subtracting in the same order. So vertically, the points should match up. So you can see above 2017 is the Y value, above 2008 is the Y value. And now I'm going to actually do that subtraction. So when I subtract on top, I got 225. And then 2017 minus 2008 is 9 years. And since this is a real world problem, we're going to divide. But if it's Not a real world problem. We usually leave it as a fraction reduce, but actually this divides out to a whole number, so we got lucky. Most of the time you get decimals. So I just got lucky and I got a whole number here. So our slope is 25. So it's positive, which means that it goes up, and you could see that on the graph. It was moving up, and then 25 is just telling us how steep it is. So this is not required for every problem that you do with slope, but it's good to understand what slope means in a real world context, and we call this interpreting slope. So our slope is 25, and when we interpret slope, we write it as a fraction, so 25 over 1. So whole numbers are written over 1. And let's take a look at what the units are. So on top, that is the number of bachelor's degrees. By women. And if we go back to our table, all right, and we go actually to the reading here, it says in thousands. So it's telling us that it's not a total of 895 degrees, it's 895,000, but we're just not writing all those zeros. So in thousands. And then in the denominator, we were dividing by number of years. So if you match up those numbers, in 1 year, 25,000 bachelor degrees were earned, or this is increasing because slope is telling you how much it's changing, and if it's positive, it's increasing. So our interpretation, we write it as a sentence, we would say the number of bachelor degrees earned by women is increasing, and it's increasing because it's positive. If I spelled that right. So that's where we're indicating the direction with the word increasing by, and then our top is 25 and it's measured in thousands. So we write our units, 25,000. That is the top of the fraction. And then we use per to indicate that division, and it's per year. And that is the bottom of the fraction. So the format is going to be very similar for any kind of real world problem. You have to first define what you're counting. So that is what I've boxed right here. That's what we're counting. And then you have to say whether it's increasing or decreasing. And that tells you, that's based if it's positive or negative. And then you say by how much, the top per the bottom, and you have to include your units. So notice that I have something per something. When I went back to, if I go back to the common applications of lines, I said something per something is generally linear. So we're estimating that the number is increasing by 25,000 per year, basically. So slope gives you useful information. It's giving you a number that you can use to predict. You can see how much is it changing. Is it positive? Is it negative? This is really important for stocks, honestly. Although stocks go up and down so much, it's really hard to do linear with them. So we found the slope, and normally, you don't have to go through all of this work. It's a lot quicker. You just simply do the calculation. Next is to actually find the equation. So first, to find the equation, you need a point and the slope. And we're going to use our first point that we had, which was the 2008, 895. So I just picked the first point, and then our slope we found to be 25. So we have a point and a slope. We're going to put it in point slope form. So I have the equation here. We're plugging in these numbers. So again, I'm using the same x1 and y1 that I had when I was finding slope. So we're putting these into our equation. We're only replacing x1, y1, and m. We're not replacing x or y. So I have y minus 895, that's y1, equals m, so that's our slope, times x minus 2008. So I plug in those numbers, and that is point slope form. Once you have it in point slope form, then you start solving for y, so that we could put in slope intercept form. So that starts by distributing on the right side. So my left side is staying the same, and then on the right, I'm multiplying 25 through the parentheses. So I have 25x, and then I need to do 25 times 2008. And it gives me a big number, that's okay. 50,200. Now I'm solving for y, so I need to add 895 both sides, which gives me y equals 25x. And then make sure you use a negative 5,200 because you've got that negative sign in there, and then plus 895, and it gives me minus 49,305. So that is my equation. And that negative value there is our y-intercept, which basically would be if x is 0. So our input is years. That would be at year 0, we're predicting negative 49,305 degrees earned by women. Now, that doesn't make any sense. You can't have negative degrees. Sometimes our equation doesn't make sense for all time. Our equation makes sense for the period of time that we're predicting for, but it may not make sense if you go far away in either direction. And that's the problem with using predictions, is that things change. They don't always follow the same pattern. Like in history, there was no such thing as bachelor's degrees, so it was just 0 for a really long time. And then bachelor's degrees were invented and it went up. So not everything means like your equation doesn't always make sense for all time. In this case, using a value of 0 years wouldn't make sense because in the year 0, the bachelor's degrees didn't exist. Negative stuff don't matter. But as long as we keep it to the time period we're looking at, this equation should be relatively accurate, assuming that you drew a good line. So now we're going to make a prediction. You don't always have to make a prediction when you go through this process, but this is a real-world application. Let's do so. Let's see what we can do with this, how this equation is useful. So we're going to just pick a year that we want to predict, and I'm going to pick 2020. So let's say I want to predict when x is equal to 2020. So you need to determine what input value you want to use. So actually, I just want to predict the year 2020. So this means my x value is 2020. Now you want to be careful how you do this, because sometimes instead of putting the full year, they might say, okay, I'm going to start the year 2000 as 0. And if we start counting 2000 as 0, then 2020 would be 20 to plug in, not 2020. So you do have to pay attention to where your starting value is. In this situation, our starting value was the literal year, so we don't have to do any conversions or anything like that. But that's just something to be aware of. So that's why I have these as separate, because sometimes the year you want to predict is not what you plug in. Now we're going to plug it into the equation, and then we're basically evaluating the right side. So our equation was y equals 25x minus 49,305. So I'm going to plug in for x the year 2020. And then I'm going to follow the order of operations. So 25 times 2020, 50,500 minus 49,305. And then I subtract is the 1195. So that is our prediction that in 2020, there will be 1,195 bachelor degrees or 1,000 bachelor's degrees earned by women. So we've made our prediction, and let's just see how close that is to the actual prediction that this website comes out. So 2020, they're using that as the last year here. That's how I matched up my data. So I want to follow this. They use 1,151. So they have a very different prediction than we do. It's they're different by less than 50. So that's not too bad, but it's a different number. And you can come up with different predictions based off of how you drew your line. If I picked 2 different points, if I drew my line a little different, I could get a different equation. So if you give the same set of data to multiple people, they could come up with different equations, and that could cause some problems because it's like, well, which one's right? So that brings us to something that is called linear regression. So linear regression is something used in statistics. It is a tool used to create a line of best fit. It's a procedure, something like these are the steps that you do, and it's a way to guarantee that everybody gets the same value so that there's one line that is the one that everybody gets. And this process generally creates a better fitting line than humans can by eyeballing it. So if I had picked different points, I get a different line, and my line may not be the best fit. What this linear regression does is it wants to minimize the distance each point is away from the line. So if I go back to my line, I had several points there that are kind of far away from my line. A line of best fit wants to make that distance as small as possible. So it draws its line differently than I did. I tried to go through as many points as possible, but it wants to minimize the overall distance. So it's just looking at it as a different way. And so there's a whole procedure for it, and this is what we call linear regression. I'm not going to go into how that works because that's in the statistics class. So we're not actually learning how to figure out that equation. There is some stuff in the book that just tells you use technology, and that's what I'm going to do here, but I'm not going to quiz you on it. It's not going to be any in your homework or anything like that. But it's just something to be aware of. So I'm going to do this in Desmos, show you what the Desmos line is, and then we can compare the difference. And for those that have to take either business statistics or mathematical statistics, you will be doing this by hand. You'll be learning the equations and everything. So that's why this class is required, because you need to know what a line is before you go to that. So I'm going to go back to my points here. Now, first, what I'm going to do is just put in my equation for a line. Y equals 25x minus, what was it? It was 49,305. 49,305. So that's what my line was that I basically drew. Picking, my eyeballed line. Now I'm going to do the linear regression line. Hopefully I remember how to do this correctly. That is not, I knew I was going to do this. Just quickly Google. Oh, okay. Instead of Y1, it's just B. I was very close. Okay. And it might be because I have a space there. I might not like it. All right. Oh, I have to put the Y1 here. Okay. I had the general idea. Okay. Let me change the color so it's a little. There we go. So the orange line is the line that technology came up with as the best fit line. So you can see it's different than mine. Their slope is 25. That's pretty close to 25.3, close to mine with 25. Their y value, or their intercept, negative 49,908, 49,305. Like, that's actually, I eyeballed a pretty good line. Usually that doesn't happen. And you can see that it goes through different points. But the orange is what technology comes up with as the best fitting line, and actually hits more points than mine does. So mine only really hit 2 points and barely touched a few others. Theirs goes through 1, 2, 2 and hits more. It looks like it hits 4, more than mine does. So slightly different with the technology. We're not going to use this equation here, but curiosity, I'm going to see what this best fit line predicts. And so I can actually do that by just typing in the math. 25.3039 we're predicting for 2020 minus 49,908.1, and they come up with 1205.778. That is a different prediction than this website comes from, but this website is using a lot more data. They're using all of these points. We are only using a small subset. And if you remove some points, your equation could change. So the more data you have, better it is. But if your data starts changing and going askew, you may not want to include those points. There's a lot of things going into statistics and why you choose some points over another and all these decisions. But this is just demonstrating technology and how we have a procedure to come up with the best line, but you can do it by hand, which is what I did. So again, if you have to go on to take business statistics or mathematical statistics, you'll learn a lot more about this. And in real life, you'll basically be using linear regression most of the time. So just to summarize what we've done, so there are 3 forms of an equation of a line. We've got standard form ax plus by equals c. This is best used for solving systems of equations, which we will do in week 8. We have slope-intercept form, y equals mx plus b, and that's generally what we use for graphing or for making predictions. And then we have point-slope form, y minus y1 equals m times x minus x1, and that's what we use when we write equations, because that's the easiest to plug into. So we got 3 forms of an equation. We essentially have 3 types of lines. We can have a slanted line, where we can write it as mx plus b. We have vertical lines, which is x equals some number. And we have horizontal lines, which are y equals a number. So those are your 3 choices. So to go back to the 3 forms of a line, if you're not sure, or the 3 types of line, whether it's slanted, vertical, or horizontal, if you don't know where it goes, solve your equation for y. And then check, is it in the form for slanted or is it in the form for horizontal? If there's no y in the equation, then it must be a vertical line, and you solve it for x, and then that gives you the form. So if y doesn't exist in the equation, it's vertical. If you have y, you need to solve for y. If you have y and x does not exist, or if x somehow cancels out, then you have a horizontal line. But solving for y is best to determine what kind of line you have. And then to summarize slope, our equation is m equals basically rise over run, change in y over change in x, or y2 minus y1 over x2 minus x1. And then to get the equation of a line, so that's what you're going to have to do on the homework, on quizzes. First, you need to have 2 ordered pairs. You need to find the slope between those points. Then you use point-slope form to get the equation, and then you solve for y. So it's essentially a 4-step process. Now, if you are given the slope, then you can skip steps 1 and 2, and you can go straight to point-slope form and then solve for y. So that is linear functions in a nutshell. Basically, you're going to be doing the same steps over and over again, finding slope, getting the equation. So you can use this as a guide, just with different numbers, but hopefully you have a good understanding of why this is useful, why you're learning this, and maybe you'll start seeing around you how linear equations really, really are everywhere, even if you don't know it. So thank you for watching this recording. Hopefully I'll have some people attend my live next week, and I will talk to you guys later.